high-speed trains are an essential part of the way we travel today, slashing journey times between major cities and bringing us in comfort to our destinations. But with our need for speed comes vital concerns about passenger safety, because when fast trains crash, the consequences can be catastrophic.
One of the most feared events in the rail industry is a runaway train, and this was one.
High-speed collisions can be explosive.
Es waren natürlich ganz schreckliche Momente für mich. Es ging dieser Lebensfilm durch den Kopf.
And the twisted wreckage of a crashed train is always a haunting sight for those who built it.
Donc je dois vous dire que chaque fois que l'on a un accident dans le ferroviaire, on est pris comme ça.
So engineers always study a disaster with forensic scrutiny, analyse critical mistakes, and devise new technologies to prevent tragedy from striking again. Quite simply, every new train under construction is being built from disaster. In April 2007, the world train speed record was broken in France with a lightning speed of 574.8 kilometers per hour. That's 200 kilometers faster than the takeoff speed of a Concorde. But when trains carry so many people at such great speeds, if there's a fault with technology, lives are at risk. In 1998, a German express train collided with a bridge, killing 101 people. In 1988, a runaway train with failed brakes smashed into a stationary train at the Gare de Lyon in Paris, killing 59. And in 1979, in the small Scottish town of Inver, an express train continued through a stop signal, causing a collision that left 5 dead. These crashes and many others over the years have brutally exposed flaws in safety technology and infrastructure, flaws that the designers of new trains are striving to eradicate. Meet the AGV. Set to roll out for commercial use in 2011, the AGV will be a modern titan of transit for the 21st century. It aims to carry French passengers in safety and comfort, distances of up to 1,000 kilometers in under 3 hours. That's the entire length of their country from top to bottom. A journey that would take 10 hours by road. The AGV is set to revolutionize the future of high-speed rail travel. The man behind this project should know. He's been in the business over 30 years. François Lacote, Technical Director of Alstom Transport, is widely regarded as the godfather of high-speed rail. And this is the prototype of his new creation. For Lacote, the AGV isn't just a train.
Ce prototype a un nom, il s'appelle Pégase. Pégase, dans la mythologie grecque, c'est le cheval ailé, c'est-à-dire c'est l'objet qui est à la fois terrestre mais déjà un peu aérien avec la vitesse, donc c'est Pégase.
Pegasus has been spreading its wings on a test track in the Czech Republic, and for months an onboard team of highly skilled train engineers have been monitoring its every move, because these people know what can happen if they don't get it right.
Nous prenons toujours en compte, nous analysons tous les événements, les incidents, les accidents, de manière à faire profiter toutes nos conceptions nouvelles de cette expérience. Nous apprenons continuellement.
The AGV is a product of years of rail disaster analysis, disasters such as the world's worst ever high-speed rail crash. On June the 3rd, 1998, in the small German town of Eschede, Intercity Express train, or ICE, number 884, was on its regular route from Munich to Hamburg. The ICE travelled at 200 kilometers per hour and had an unblemished safety record. On this day, 287 passengers were on the train, among them Udo Bauch, who boarded at Hanover station.
Meine Frau hat mich an diesem Tag um 9:05 Uhr an den Bahnsteig gebracht. Dort bin ich in den ICE eingestiegen. Ich saß im zweitletzten Abteil, erste Klasse, und habe im Abteil mich auf eine Tagung vorbereitet mit meinem Laptop.
It seemed a perfectly normal journey for Udo Bauch and his fellow passengers as ICE 884 travelled on towards Hamburg. But about half an hour in, passengers in the front car began to notice unusually heavy vibration. And then a piece of metal broke through the floor. Although the train now felt dangerously unstable to the passengers, the problems went unnoticed by the driver, who continued at top speed. As the train travelled on another 5 kilometres, passengers attempted to alert him. But it was too late. The train suddenly derailed, smashing into the supports under a road bridge.
Eine Vorwarnung hatte ich nicht. Es hat auf einmal einen Schlag getan, wo ich noch nie im Leben erlebt habe. Es ging auch sehr, sehr schnell. Es hat mich in Sekundenschnelle im Zugabteil umeinander geschlagen, von links nach rechts, von oben nach unten.
The impact of the collision caused the bridge to collapse. As the train jackknifed, 300 tons of concrete came down on top of it. Hundreds of passengers were trapped inside the crushed carriages. As the dust settled on the twisted wreckage, local policeman Andreas Effinghausen was one of the first on the scene.
Als wir hier ankamen, haben wir nur diesen kaputten Zug gesehen, völlig zerstört. Und ansonsten gar nichts, es war nichts zu hören. Ja, mein erster Eindruck war natürlich, dass sich wahrscheinlich aus dem Zug keiner lebend rausgekommen ist, so wie das aussah. Dass es wohl eine hohe Anzahl von Toten geben würde.
Although there seemed to be little sign of life amid the carnage, Effinghausen set out on a search for survivors.
An einem Punkt, da habe ich gestanden, habe da reingeschaut und habe aus irgendwelchen Gründen, die ich heute nicht mehr weiß, Hallo gerufen. Und dann hat mir jemand geantwortet und das war der Udo Bauch.
In the crumpled wreckage that was the second to last carriage lay passenger Udo Bauch. Amazingly, he was still alive.
Ich habe mich kurz nach dem Aufprall wiedergefunden, dass ich eingeklemmt war. Ich habe gemerkt, mein linkes Bein war eingeklemmt. Ich lag am Boden, im Zugabteil am Boden und habe natürlich sehr, sehr starke Schmerzen gehabt. Und das waren natürlich ganz schreckliche Momente für mich. Es ging dieser Lebensfilm durch den Kopf, wo ich an die Kindheit gedacht habe, an die Familie. Und das war schrecklich.
Für mich so ein Wunder, dass überhaupt jemand geantwortet hat. Und das hat auch so ein bisschen die Lebensgeister in einem geweckt, das muss man so ganz ehrlich sagen. In dem Moment wurde ich auch dann richtig aktiv und habe versucht, von den mittlerweile hinzugekommenen Rettungskräften irgendwelche zu erwischen, die dem Udo da helfen und ihn da vielleicht rausholen.
Although seriously injured, Udo Bauch was eventually freed from his mangled carriage, but many others were less fortunate. 101 passengers died in what remains the deadliest high-speed rail crash in history.
Der Unfall von Eschede veränderte mein Leben total. Ich bin als kerngesunder junger Mann in den Zug eingestiegen, habe mich auf eine gute Beförderung verlassen und bin als Schwerbehinderter hier rausgekommen, kann nicht mehr arbeiten, kann viele Dinge des täglichen Lebens nicht mehr machen. Insofern hat es mein Leben total verändert.
Engineers were determined to find out what had caused this devastation. Finding the answer would be essential for the future of rail safety. It was clear that something had gone catastrophically wrong in the minutes before the crash. Investigators found the first clue on the front carriage. It was discovered that one of the rear wheels had failed and was left bent and broken. More clues were found on the track stretching back from the crash.
They found that there was damage to the track for quite a long distance, suggesting that there'd been at least a partial derailment.
But what had caused the wheel to derail at such high speed? As investigators continued to examine the track, the next piece of the puzzle fell into place.
5 kilometres back from the accident site, they discovered shards of rubber, which they determined had come from dampeners on one of the train's wheels.
To learn more, investigators turned their attention to the construction history of the ICE train. 7 years earlier, test runs had identified a problem with the train's monoblock wheels. Made from a solid single cast of steel, monoblock wheels were standard on high-speed trains at the time, but they caused serious vibration in the ICE's carriages.
Ich habe selber bei einer Fahrt oder bei 2 Fahrten mit dem entsprechenden ICE die Vibration in einem solchen Wagen, der solche unrunden Räder hatte, gespürt. Das wirkte auf die Bauchdecke und führte zu einem Erbrechensgefühl, sodass die Passagiere beim Erreichen einer bestimmten Geschwindigkeit bei diesem Zug schlagartig die benachbarten Wagen aufsuchten und nicht mehr in diesem Wagen sitzen wollten und konnten. Die Vibration bei den Passagieren und deren Unwohlseingefühl musste behoben werden durch eine neu einzubauende Komponente.
Fearing a huge loss of revenue from passengers unwilling to ride on such noisy and uncomfortable trains, the ICE's operators, Deutsche Bahn, urgently looked for a solution. They found what they thought was the answer on a tram. Trams had been using rubber-cushioned resilient wheels for years to reduce noise and vibration. Unlike the monoblock wheel, the resilient wheel consists of 3 parts: a central steel core, rubber pads to dampen vibration, and a steel rim mounted on the rubber.
These so-called resilient wheels are able to flex slightly and therefore absorb noise and vibration, and been used very successfully and for a long time on low-speed applications, particularly city trams. But to extrapolate their use to high-speed trains was a big step.
In their choice of the resilient wheel, engineers had solved the immediate problem of ICE's passenger comfort, but they'd unwittingly created a new problem. Resilient wheels were safe on relatively low-speed trams, but they had a much greater chance of severe metal fatigue at high speed than solid monoblock wheels. With every high-speed rotation of a steel rim mounted on rubber, the metal gradually weakens.
If the rim was on a solid hub, like this pencil lying on the desk, and we apply a load to the outside of the rim, then the rim can't deflect and is supported by the solid hub. If, however, it's supported on rubber pads, now we deflect the rim and tensile stresses develop on the underside of the rim of the wheel. Eventually, the stresses were sufficient to cause a fatigue crack. So the crack grows by a tiny amount with each repetition of the load until eventually it is so big that the pencil breaks. During the service of the wheel, very careful examinations are made using very sophisticated apparatus, but it's always focused on looking for cracks initiating in the contact area between the outside of the rim and the steel rail. In a solid wheel, that is where we'd expect fatigue cracks to grow. But because of this flexible rim and the bending stresses being a maximum on the underside of the rim, this is out of sight and out of mind and not being looked at by the inspection process.
During its lifetime, the resilient wheel on ICE 884 had travelled over 1.8 million kilometres. But tragically for the passengers on June the 3rd, 1998, this was its last journey. A severe stress fracture in the steel rim caused it to rupture and detach from its steel core. The rubber pads disintegrated, and the broken rim jammed up into the carriage.
That was the part of metal that had gone through the floor of the carriage, alerting the passenger to the danger.
The train was able to continue in this unstable condition for another 5 kilometres, but when it approached a set of track points with a guide rail, disaster was certain. The other end of the broken wheel rim caught on the guide rail, ripping it up and out of place, derailing all the carriages behind.
The train was then being pulled by 2 different forces. It was trying to go straight on, but the wheels were pulling it sideways.
The first 3 cars decoupled and continued under the bridge. But the remaining carriages now had nowhere else to go but straight into it. The collision was so extreme that the bridge completely collapsed on top of the train. So a combination of a broken wheel rim and the proximity of the guide rail to a 300-ton concrete bridge resulted in the largest death toll in high-speed rail history.
Discover the past with exclusive history documentaries and ad-free podcasts. presented by world-renowned historians, all from History Hit. Watch them on your smart TV or on the go with your mobile device. Download the app now to explore everything, from the wonders of ancient Pompeii and the mystery of the princes in the tower, to the life of Anne Boleyn and D-Day. Sign up via the link in the description.
After the crash, many changes were made by the German Federal Department of Railways. The Eschede disaster showed that if a train is partially derailed, it's most likely to suffer complete derailment when it reaches a set of track points. So it was decided that all track points should be moved away from bridges and other potentially hazardous structures. Additionally, with its high-speed design flaw now starkly exposed, the resilient wheel had had its day.
After the accident, these resilient wheels were withdrawn from service, and I think it's highly unlikely that they will ever be used again for high-speed train applications.
The rail industry always learns from rail accidents, and one of the lessons from this one was that the resilient wheels used on these ICE trains were unsuitable at the high speeds that the trains go. They were fine on trams, but not on the ICEs.
The resilient wheel was replaced by the more trustworthy solid monoblock wheel. But although the broken wheel was the root cause of the accident, there was a major additional factor that made the outcome far worse than it might have been. The twisted wreckage of ICE 884 was chilling proof that the train's structural integrity had been seriously inadequate.
One of the things that made it worse was the way that the carriages jackknife, piling into each other and crushing the people inside.
The ICE carriages were made of a lightweight aluminium body shell welded to a heavy steel underframe. As the carriages concertinaed into themselves on impact with the bridge, many split along the weld lines as if by a tin opener, crushing passengers inside or spitting them out onto the track. It was clear that the train just hadn't been designed to withstand a high-speed collision. According to Dr. Kuhlwetter, a retired lawyer for the Federal Department of Railways, design practices have now changed.
Heute wird ein Fahrzeug konstruiert, nicht nur bei der Eisenbahn, sondern auch beim Auto, auch beim Flugzeug, mit äußerster Ausnutzung der Materialtragfähigkeit. Man konstruiert mit Grenzwerten, man konstruiert mit dem Computer. Früher hat man Fahrzeuge gebaut mit, ich sag mal, dem dicken Daumen.
Like the ICE train, the AGV has welded aluminium body shells for their weight advantage. But the difference is, before they were even built, the AGV carriages were tested to their limits using advanced computer modelling.
Et donc nous avons besoin d'une caisse très rigide. Et pour cela, on emploie les outils normaux de l'ingénieur, à savoir du calcul de structure, de la modélisation par, comme on appelle, par élément fini, de manière à pouvoir modéliser l'ensemble de la structure et ensuite l'ensemble de la réponse de la structure.
The AGV's engineers would rather not wait until a crash to know how their carriages will respond. So calculations are made based on the property limits of the materials used and the potential forces exerted in a collision. With this information, engineers strive to perfect their design for maximum safety. But the key to the AGV's crashworthiness isn't just in the individual strength of its carriages, but in the rigidity of the train as a whole. This is achieved by addressing the very same problem that Deutsche Bahn were trying to solve with the resilient wheel on the ICE, vibration.
Nous faisons des calculs prenant en compte les deux situations, le vibratoire et la sécurité en cas de crash, de manière à avoir la structure qui réponde aux deux considérations.
On all trains, the wheels are housed in a chassis known as a bogie. On conventional trains, including the German ICE fleet, these bogies are located at the front and back of each carriage, directly below the passengers. Reducing vibration here depends heavily on good suspension. But the AGV has what are known as articulated bogies, which are located under the vestibules between carriages, moving the bogies away from the passengers eliminates the majority of vibration and rolling noise on board. But the bonus of the articulated bogie is that not only does it solve the issue of passenger comfort, its very positioning contributes to the rigidity of the train as a whole in the event of a derailment.
Et vous avez les deux voitures, une là, qui sont très solidement connectées par une articulation, et c'est ce qui fait la clé à la fois des qualités aérodynamiques et de confort, mais aussi de sécurité du train. C'est pratiquement indissociable.
The couplings on the ICE train were not very different from this old train, where the bogies are separate on each carriage, and that means there's the real potential in an accident to jackknife like this. Whereas if you have modern articulated bogies, the train is held rigid and can't jackknife in that way.
When carriages are mounted on conventional bogies, like ICE 884, in the event of a derailment, there's potential for significant pivotal movement between them. If one car derails in a certain direction, the momentum can cause the next one to jackknife the opposite way, as was the case in Eschede. But the positioning of the articulated bogies on the AGV means the carriages are strongly supported at the point of pivotal movement, making for a far more rigid train. So if one car derails and moves in a certain direction, the one behind is pulled the same way. Articulated bogies were already in use on the AGV's predecessor, the TGV, at the time of the Eschede disaster, and proved their worth dramatically 5 years earlier.
Nous avons eu un effondrement de terrain localisé sous la voie et le train à grande vitesse est passé à 300 à l'heure au-dessus de cette zone où la voie n'était plus du tout tenue. C'était une voie complètement non stabilisée. La motrice, le premier véhicule de la motrice est passé, tout le reste du train a déraillé et ça s'est très très bien comporté. Le train ne s'est pas couché, le train, grâce à notre système articulé, le train ne s'est pas désassemblé. Il n'y a eu pratiquement aucun blessé.
But the AGV has a remarkable innovation over the TGV. Like most trains, the TGV is driven by locomotive engine cars at either end of the train set, which move the inert carriages in between. But the AGV has no need for engine cars, because its carriages can move themselves.
C'est tout à fait nouveau. La motorisation de la GV se fait, comme on l'a dit, avec une motorisation répartie, ce qui signifie que nous avons installé les moteurs de traction directement à l'intérieur du bogie. Ici, vous avez le moteur, c'est un moteur de nouvelle technologie, un moteur à aimant permanent. Le gros avantage, c'est que c'est un moteur très puissant, petit et léger.
Never before has a high-speed train motor been powerful enough and small enough to fit directly inside an articulated bogie. Distributing these powerful lightweight motors across the train in this way is what makes the AGV capable of its blistering speed. In fact, the AGV's revolutionary bogies were used to set the new world train speed record in April 2007. Lacote created a super-fast hybrid train by sandwiching two of his trailblazing bogies between two TGV locomotives.
Il faut dire que lorsque l'on a dépassé la vitesse du précédent record, qui était 515 à l'heure, nous étions très heureux. Nous voulions repousser les limites, et ce sont des limites qui sont liées à la voie, qui sont liées à la dynamique du train, qui sont liées à l'aérodynamique, qui sont liées au captage du train avec la vitesse critique de la caténaire. On ne pouvait pas dire qu'on était certain. On avait une expérience, on avait des modélisations, nous avions fait des calculs, nous étions confiants, mais pas certains.
But not only is this new power bogie good for speed, there's a big advantage for the stability of the train set too.
Le fait que les moteurs soient très bas, ça va dans le bon sens vis-à-vis de l'abaissement du centre de gravité. Donc tout ceci concourt à avoir un train très stable.
Positioning the weight of the engine as low as possible in the train makes it far more likely to remain upright in a derailment. But for all this groundbreaking engineering, rail safety has always relied, and will always rely, on one simple principle: being able to stop. On June the 27th, 1988, commuters were making their way home from the underground platforms at the Gare de Lyon, one of Paris's busiest stations. Among the crowds was Dominique Pavie.
Je rentrais chez moi, Villeneuve-Saint-Georges, donc du musée du Louvre à Villeneuve-Saint-Georges, je passais par la gare de Lyon. Il était assez tard, Arrivé à la gare, je trouve un omnibus qui allait partir. Je monte dedans, dans la deuxième voiture. Cet omnibus ne part pas. On nous annonce qu'il y avait des pannes, des retards, etc. Il faisait chaud. Il était bondé, il était plein de gens. Et puis j'attendais, comme tout le monde, assise.
But as Dominique waited for her delayed train to depart, she saw a quicker way to get home.
Puis je vois arriver sur le quai d'en face un direct pour Villeneuve-Saint-Georges où j'habitais. Donc j'ai décidé de quitter l'omnibus qui ne partait pas. Enfin, je suis arrivée à descendre. J'ai fait 5 pas en direction de la tête du train. 5 pas sur le quai. Et au 5e pas, il s'est passé quelque chose que je n'ai pas tout de suite compris. Ce que j'ai perçu en premier, c'est un bruit sourd et métallique. Une fumée noire, une poussière noire.
In her split-second decision to leave her delayed train, Dominique Pavie avoided a catastrophic collision. The train she had just left was hit with colossal force by a runaway train, completely crushing the carriage that she'd been in just moments before.
Lorsque la poussière retombait, ce qui m'a le plus frappé, c'est ce qu'on appelle le silence de mort. Et ce qui est extrêmement douloureux, c'est qu'après sont arrivés les gémissements, des gémissements vagues, tout doucement, des pauvres malheureux qui étaient écrasés. J'ai perçu évidemment des choses pour lesquelles je n'ai pas de mots.
The impact was so severe that the front carriages embedded in each other, making it difficult for rescuers to tell which train was which. 59 people were killed in the disaster, and many others were seriously injured. So what had caused this extraordinary collision? Why had a runaway train come into an occupied platform? And crucially, why had it not been able to stop?
One of the most feared events in the rail industry is a runaway train, and this was one. But the question was, why had the brakes failed?
The person charged with finding the answers was seasoned disaster investigator Jean-Pierre Pascal.
Ce qui est certain, c'est que le train qui a tamponné est descendu dans la gare souterraine qui est en profondeur avec une pente très forte de descente sans ses freins mécaniques.
Upon inspecting the wreckage of the runaway train, Pascal noticed something very unusual with the mechanical air brakes.
Le robinet qui contrôle toute la conduite d'air comprimé du train, qui se trouve juste derrière la motrice de ce train, était fermé. Il aurait dû être ouvert, ce robinet. Normalement, lorsque la conduite est coupée de cette façon-là, le système pneumatique est fait de telle façon que tous les freins de toutes les voitures qui sont derrière se bloquent automatiquement et le train ne peut pas partir.
But why was the valve closed? And if the brakes were locked on, how was the train able to move? A few days after the accident, a passenger came forward and admitted pulling the emergency cord, which automatically applied the brakes, because she'd forgotten to get off the train as it was pulling away from her stop, 10 kilometres before the Gare de Lyon. The investigation quickly shifted focus to the delay that this had caused at the suburban station. Resetting the brakes after an emergency application should have been a simple procedure for the driver, but it was discovered that in doing so, he had inadvertently closed the air brake valve, locking the brakes on. In his desperation to unlock the brakes, the driver then made a critical error.
Comme il ne pouvait pas partir, il a, on appelle ça, purgé le système, c'est-à-dire que, parce qu'il y a un réservoir d'air qui reste gonflé, même si la conduite est coupée, et qui serre les freins. Et si on veut desserrer les freins, on peut ouvrir une petite trappe, une petite fuite sur ce réservoir et le vider. C'est ce qu'il a fait.
In order to fully unlock his brakes, the driver systematically bled the air from the air brake reservoir of each and every carriage on the train. It worked, but and he was finally able to drive away. But the driver had no idea that with the air valve still closed, he was speeding towards Gare de Lyon with brakes that were unable to replenish.
À 3 km, on s'aperçoit, il essaye de ralentir, le conducteur, il s'aperçoit que les freins ne marchent pas. Il prévient par radio le centre de contrôle de la gare de Lyon il sait où il va, il sait qu'il va descendre, qu'il va aborder une descente très forte et que son train ne s'arrêtera pas.
An accident was now unavoidable, but at this stage, a collision wasn't.
There had still been one last chance to avoid a collision with another train. The control system in the Gare de Lyon area has a safety feature to ensure that no train can be directed into an already occupied platform. But unfortunately, investigators discovered that once the control centre heard about the runaway train, they locked down the whole system.
In order to keep all other trains out of harm's way, the control centre initiated what's called a general closure procedure, which gave them complete manual control over the usually automated routing system. They now had the ability to switch every signal to red, freezing all other train traffic into the Gare de Lyon. But in overriding the automated system, they'd made a disastrous error of their own. They had disabled the one automatic safety feature that would have directed the runaway train into an empty platform. Disaster was now inevitable. The speeding train ploughed into the waiting train, crushing the front two carriages. Dominique Pavie can't quite believe she survived.
J'ai eu vraiment la sensation d'avoir évité la mort à 5 secondes. Et une mort horrible parce que j'étais au début du deuxième wagon, donc j'aurais été complètement écrasée en accordéon, quoi. Ça c'est sûr, c'est sûr. Donc vraiment, pour moi, j'ai frôlé la mort de très très près, quoi.
Ce sont des choses, c'est catastrophique, mais comment dire ça n'arrivera jamais? On ne peut pas le dire. On ne peut pas dire que ça n'arrivera jamais. Ce qu'on peut dire, c'est que tout est fait pour que ça n'arrive pas.
After the Gare de Lyon incident, many changes were made to rail systems across Europe. Air brake valves were removed from engine cars, and passenger-activated emergency brakes were replaced with emergency driver intercoms to ensure that only the driver is able to stop the train. Changes were also made to the general closure procedure at French main stations, so that staff could manually operate the signalling system without overriding pre-programmed automatic routing features. But the top priority for engineers was to eliminate the risk of brake failure altogether. Among the technological safeguards in the AGV is a braking system in which it is not possible to bleed air from the main brakes. For one good reason. There is no air. Instead, the very thing that powers the train is also what breaks it.
Ce moteur à aimant permanent fonctionne en général comme moteur, mais il peut fonctionner en générateur comme une dynamo. C'est-à-dire qu'avec l'inertie du train, la dynamo oppose de la résistance au mouvement et cela freine le train et en même temps cela crée de l'électricité. Donc un seul objet et deux fonctions, soit traction, soit freinage.
Using a motor in this way is known as dynamic braking. By simply reversing the magnetic field of a motor, huge resistance is imposed on a train's forward momentum, slowing it down and generating kinetic energy. This energy is normally wasted as heat through overhead resistors. But the AGV has a remarkable alternative use for it. These brakes are regenerative, which means the braking energy created is not wasted as heat, but returned from the train to the national grid as electricity. In fact, up to 20% of the AGV's electrical consumption can be recovered with regenerative braking, energy efficiency that Le Cote is extremely proud of.
Donc on produit de l'électricité, on renvoie l'électricité à travers la caténaire au réseau public, et avec ça on peut vendre notre électricité, on peut faire un peu d'argent en freinant ce train.
The AGV's regenerative brakes improve safety as well as profits. As this is an electric, not a compressed air system, the AGV simply cannot be bled of its braking power, as was the runaway train at the Gare de Lyon. No matter how effective a train's brake system, the possibility of a head-on collision can never be completely eliminated. Somehow, passengers have to be protected from the violent forces of a potential impact. Engineer Thierry Yonnet has devoted a career to this challenge, and he's now helped to devise a revolutionary crash shock absorber that's built into the nose of the AGV.
Donc c'est un système anti-collision. En cas de collision, on va absorber successivement par 3 modules une partie de l'énergie.
A huge volume of energy is generated by a high-speed impact, and it's the task of an anti-collision system to absorb as much of it as possible. Yonnet's system does this in 3 phases.
Dont le premier est essentiellement un système d'usinage mécanique. Si on s'en approche, on peut voir qu'on a tout un système de fixation de ce coupleur sur une plaque. Et cette plaque, elle, est maintenue par 4 vis qui servent de fusible mécanique. En cas de choc violent, ces vis vont casser, elles sont là pour ça, elles vont céder. Et l'ensemble, tout l'ensemble, va se propulser à l'intérieur.
After these fuses have broken, a second absorption system consisting of a large steel buffer absorbs additional energy. And behind that is a third system of pre-folded steel plates designed to crumple. The total energy absorbed helps maintain the structural integrity of the train. But if train journeys are to be made completely safe, advances in train design have to be matched by technology on the line. It was a quiet morning on October the 24th, 1979, in the small Scottish town of Inver on the banks of the Tay estuary. Katrina Wright and her mother were on a train bound for Dundee.
We were going through to Dundee, me and my mum. We were sitting second carriage from the back, and we were just going Christmas shopping early. It came to a halt just after Inver station. It wasn't due to stop there, so we wondered why it had stopped. And then the guards told us that it had broken down.
But what Katrina and her mother didn't know was that a Glasgow to Aberdeen express train was heading straight for them at 70 miles per hour. The guard on the speeding express train, George McRitchie, was riding in the brakes van.
Coming around the bend when I seen it on the little train in the line, I didn't think it was on our line. I thought it was on the coming towards us, but here it was on our line. Next thing, I went to put the brake on.
But as McRitchie scrambled for the emergency brake in his van, it was too late.
The express had a quarter of a mile to stop, but it didn't, and collided with the rear of the first train with such force that both reared up in a tangle of tearing metal.
The tables and everything got turned, and we got thrown about all over the place, and then it came to a halt.
The impact of the collision was so severe that it catapulted the back 4 carriages of the stationary train over the sea wall and into the estuary.
There was complete silence, and then everybody started screaming and crying. It would have been much worse if the tide had been in. So I don't think we would have made it, to be honest.
Had Katrina's train plunged into water, she and the others in her carriage would almost certainly have drowned. But as it was, the soft mud in the bay cushioned the impact. Up on the track in his now derailed brake van was George McRitchie.
Bumped my head and sort of stunned. You know, and when I come to, I said, "Oh, Jesus!" I got looked outside. I said, "Oh, Jesus!"
The 2-man driving crew of the express died on impact. The senior driver had been a close friend of McRitchie's.
That's when I seen my driver and second man lying there. And I took a tarpaulin and covered the bodies up. And boom, had a hole right in the middle, as if he'd been shot, where he'd hit his head when they applied the brake.
3 more died in the rear carriage of Katrina Wright's train, taking the death toll to 5.
It does give me a lump in my throat, because you think of the loss of life and just people doing their normal job and unfortunately not going home at the end of the day. It's quite tragic, yeah. And to think we actually came out of that alive.
So what was it that had brought such tragedy to the quiet town of Inver?
Once again, the inquiry team will begin their investigations, this time concentrating on the signalling system here, which may have led these two trains to disaster.
The investigation started 2 miles back at the signal box in Long Forgan. The type of signals in operation here were of the old semaphore variety, common on railways all over the world at this time. If the signal's arm is raised to an angle of 45 degrees, the driver may proceed. If the arm is horizontal, the signal is at danger, instructing the driver to stop. Long Forgan had a typical setup, consisting of an initial distance signal to warn the driver to slow the train, a signal box for operating the signals, and a second signal further down the line to bring the train to a complete stop. On the day of the crash, John McRae of the Tayside Fire Brigade came to investigate the signals at Long Forgan.
And we discovered there was a signal down there, just beside that tree, roughly in that area, so we know, but there was a signal there, and the signal was showing an incorrect signal, inasmuch that rather than being horizontal for stop or 45 for go, it was halfway between.
McRae discovered that although the signalman had set the lever in his box to danger to halt the express, the semaphore arm did not in fact return to the full horizontal stop position. The driver interpreted the ambiguous signal as go and accelerated on towards Inver, unaware of the stationary train on the line ahead. Disaster was now imminent. As the express train came round the bend at 70 miles per hour, it couldn't possibly stop in time, colliding with the stationary train and smashing its back four carriages into the bay. But why had the driver continued through an ambiguous signal? In the official report into the crash, it was suggested that a driver's changing angle of vision to an ambiguous signal could possibly affect his reading of it. Railway signalling expert Roy Bell is setting out to recreate what the driver may have seen.
We're approaching a signal now which is imperfectly shown. A driver would normally not take this as proceed. However, as we get closer to the signal, the angle as we're viewing it changes, and it is possible, just possible, that a driver might take the signal as proceed. And that's what, in my opinion, happened at Inver.
The driver had clearly been let down by an archaic mechanical system, but engineers needed to know exactly how it had failed him.
Traditional semaphore signals have been used on railways for well over 100 years, and they're simply operated by a lever being pulled.
When a signal lever is pulled, a system of cogs and chains at the signal box controls a wire that runs to the signal post, adjusting the angle of the arm. So why was the signal arm at Long Forgan at such a strange angle?
Could have been in the position it was because it had been a cold night and the tension on the wire had increased as the temperature got colder, which meant that it wasn't so easy for the signal to return to the full horizontal stop position.
When questioned, several signalmen who worked at Long Forgan admitted having problems with the same signal during periods of cold weather. If one cold night could cripple the mechanics of the semaphore system and cause such devastation, it was time to re-examine signalling technology. Immediately after the accident, the Long Forgan signal box and many others across the country were fitted with repeaters, which indicated the exact position of the semaphore arm to the signalman, so that he'd know if it had malfunctioned. But the mechanical flaws of the semaphore system had been exposed, and gradually these signals were phased out in favour of colour lights with less potential for ambiguity and significantly lower maintenance costs. But surprisingly, they haven't stopped signalling disasters. In other accidents, sunlight, shadows and scaffolding have all been cited as factors in obscuring a driver's view. It remains clear that any form of signalling still carries with it the possibility of a driver passing a signal at danger. Engineers in Europe are now developing a radical new idea for signals, getting rid of them altogether. and their system involves such advanced technology that in the future, the high-speed train driver himself may also be a thing of the past.
Already, the technology is there for trains to travel at hundreds of miles per hour without a driver.
A revolutionary train protection system is now being implemented in Europe that will make passengers safer than ever. It's called the European Rail Traffic Management System, ERTMS.
At the moment, trains are controlled by outside signals, which the driver has to see. The crucial point about ERTMS is that signals will be directly transmitted into the train's control system so that they can't possibly be overridden or missed by the driver.
A unique satellite radio communication system transmits signaling instructions from a control center directly to a computer in the driver's cab, called the European Train Control System, ETCS. The computer uses this information to calculate the safest maximum speed at which the driver can travel. If the driver disobeys the computer, it will automatically slow the train to within the safe limit. The ETCS onboard computer virtually eliminates the possibility of a signaling disaster. But there are other benefits too. A fully equipped ETCS train constantly transmits its location to the control center, allowing trains to run closer together and line capacity to be increased without safety risks. This groundbreaking technology is already in its infancy in more than 10 different countries and is set to be installed on all European high-speed lines in the future.
Once ETCS is introduced throughout Europe at its highest level, it will be the end of an era for railway signalling, because essentially the trains will be controlled from outside rather than from in the cab.
If computers are now in control of high-speed trains, it could be argued that there's no need for a driver. The AGV is equipped with ETCS technology, but François Lacoute is not about to let his driver go.
Donc cette association entre l'automatisme vis-à-vis de tous les événements prévus et de l'homme qui sait réagir face à un imprévu, c'est ça qui maintenant va faire la sécurité absolue du train à grande vitesse. Ça doit rester la solution. Le conducteur reste indispensable à bord.
There are a number of driverless services operating around the world, but they exist as relatively low-speed metro links. As yet, there are no driverless high-speed trains in commercial operation. But some suggest that's not because of the limitations of technology. It's psychological.
People will not accept the idea of a train being driven at several hundred miles an hour along busy tracks with lots of other trains without there being a driver there to reassure them that their journey will be safe.
Whatever the future for the high-speed train driver, there's no doubt that the huge advances in safety technology have made the possibility of disaster increasingly remote. And as European high-speed lines embrace this cutting-edge safety system, François Lacoute is proud to have a train that's ready for the challenge.
Je voulais le train pour le réseau ferroviaire à grande vitesse de l'Europe, c'est-à-dire un train complètement européen, capable de toutes les lignes ferroviaires de l'Europe et un train capable de la vitesse du futur, c'est-à-dire au moins 360 km/h. C'était le train du futur de l'Europe.
The AGV is certainly a high-speed train for the future, but that's only because it's a product of the disasters of the past. Tunnels, a miracle of modern engineering. They make mountains manageable, connect our cities, and can even bring together continents. Places of mystery and adventure, and occasionally, catastrophic disaster. Since the tunnel building boom of the 1960s, the world has become a very different place. More people, more trucks, more traffic, more accidents. The past decade has seen tunnel disasters that have spelt destruction, chaos, and even death.
Sie sind alle in den ersten 10 Minuten erstickt.
We all got out on the Italian side. The people on the French side were not so fortunate.
While investigators pick through the ashes to find out what went wrong, the engineers of new tunnelling projects figure out how to put it right.
We have to eliminate catastrophic failure.
Across the world, the modern tunnel is built from disaster. Tunnels bring people together, connecting towns, countries, and even continents. But the world's tunnels are under pressure. As more traffic and freight passes through them, accidents are on the increase. 1999, a burning truck was abandoned in the Mont Blanc tunnel that connects France and Italy. 39 people died. In 2001, a truck collision in the Gotthard tunnel caused a massive fire. 11 people died. 1996, a burning cargo train caused the lining of the Channel Tunnel to explode. Serious structural collapse.
They said that the concrete was falling on them like shrapnel.
From each event come crucial lessons in tunnel design, revised approaches to evacuation and fire control, new construction techniques to prevent tunnel collapse, fresh ideas about accident prevention. Across the world, new tunnels are being built from disaster. One of the most innovative new tunnelling projects is the Marmaray Tunnel, under construction in Istanbul, Turkey. At an estimated cost of $3.5 billion, the 13.6-kilometre long tunnel system will run 58 metres under the Bosphorus Straits. It will be the deepest immersed tunnel in the world. Istanbul needs the tunnel badly. It has a population of 12 million and terrible traffic problems. It will take the pressure off the Bosphorus Bridge and will be the first tunnel connection between Europe and Asia.
The Marmaray project will make the lives of the Istanbul citizens more comfortable and will save them a lot of travel time.
The tunnel's designers have much more to consider than commuter comfort and reduced journey times. Their biggest challenge, as for any tunnel construction, is how to overcome fire, a tunnel's single greatest threat, as recent disasters have shown. On March the 24th, 1999, 2,000 kilometres away across Europe, a sequence of events began to unfold that was to have fatal consequences and would influence the design of all new tunnels to come. At 10:46 in the morning, a heavy goods vehicle entered the 11.6-kilometre long Mont Blanc tunnel, which connects France and Italy. 6.7 kilometres inside the tunnel, the driver was shocked to discover his truck was on fire.
J'ai regardé mes rétroviseurs et j'ai vu de la fumée du côté droit. Je suis sorti du camion, et la fumée était déjà beaucoup plus importante. J'ai voulu prendre l'extincteur, mais je n'ai plus l'occasion parce que ça a éclaté en feu, toute la cabine.
The driver abandoned his vehicle and managed to escape, but he left behind a disaster in the making. A burning truck with a highly flammable cargo. One of the drivers also using the tunnel that day was British trucker John Whitby.
In a period of 18 months, I probably used the Mont Blanc about 40 times. It was a dark, depressive type of tunnel. It seemed to go on forever.
Whitby entered the tunnel on the Italian side, en route for France.
I was driving for about 5 minutes into the tunnel, and then we started to get traffic approaching that was flashing its lights.
Moments later, around 40 vehicles were forced to a halt, including Whitby's truck.
We stopped, we got out of the vehicles, and we were looking down the tunnel to see what was going on ahead, whether it was roadworks or whatever, and it was all black. So we just assumed that the lights had gone out further down the tunnel.
Within minutes, the Italian emergency services began to arrive.
The fire brigade came roaring into the tunnel, and they shot straight past us, sirens going, and just disappeared into this wall of blackness. And it was only about then that we started to think, well, that black might just be smoke.
The abandoned truck was carrying margarine, highly flammable, and by now, burning hot and fast. As the tunnel filled with smoke, there was a series of loud explosions.
Like a field gun in the distance. We've got a fire on here. There's that's truck tyres exploding. The entire tunnel actually shook. The road shook under the feet. You felt the air vibrate and the walls shake.
Whitby and others near him were rescued by an Italian fire engine, forced into retreat as the fire escalated.
And we all got out of there at a very rapid rate of knots.
Those nearer the French exit were less fortunate. The smoke surged towards France, stopping the French fire team from entering.
Et à leur arrivée, il y avait déjà plusieurs kilomètres de tunnels enfumés. Et les premiers intervenants ont été bloqués dans le tunnel.
The drivers on the French side of the blaze were trapped, enveloped in thick smoke.
The lucky ones died in the cars. They probably 2 lungfuls of the smoke and they were dead. It was that toxic and that thick.
Some drivers on the French side managed to leave their cars for the supposed safety of the tunnel's fire refuge cells. But these were designed to deal with a small car fire, burning at 800 degrees centigrade for only a few hours. At Mont Blanc, the fire blazed at 1,000 degrees centigrade for 53 hours.
And these poor people were basically cooked inside the safety cell. And I honestly cannot think of a worse way to die.
It took 5 days for the tunnel to cool down before the fire services could enter. They were horrified by what they found.
Pour l'incendie du tunnel du Mont Blanc, il y a eu des températures jusqu'à 1000 ou voire 1200 degrés qui ont été atteintes dans certains secteurs du tunnel. Et donc, en arrivant sur les lieux du sinistre, après avoir refroidi la voûte, nous avons découvert progressivement plusieurs dizaines de véhicules totalement calcinés, hein, puisque, je le répète, les températures sont montées à plusieurs centaines de degrés, voire à 1000 degrés. Donc, des restes de véhicules, de tôles, de carcasses de véhicules sur plusieurs centaines de mètres de long. Et notamment sur 600 mètres, même l'asphalte de la route avait fondu et brûlé.
Of the 50 people caught in the fire, 39 died.
When I think back now, I was probably one of the 11 luckiest people in the world. It's an experience that will never ever leave me, because those people shouldn't have ever died. None of them should have died.
The Mont Blanc fire was a tragedy that drew worldwide attention. An investigation began into what had gone wrong. Part of the answer lay in changing times. Built in 1965, the Mont Blanc road tunnel was designed to carry light traffic, not heavy goods vehicles. Wind forward to the late 1990s, and a different world uses the tunnels of Europe. Part of this new economic order is the container truck, often carrying flammable materials. The old Mont Blanc fire refuges and ventilation system simply couldn't cope with the intensity of a modern truck fire. Since 1999, the Mont Blanc tunnel has been redesigned and refitted along its entire length. When the truck caught fire, smoke and toxic fumes rapidly accumulated in the tunnel, with catastrophic consequences. As atmospheric pressure was lower on the French side than the Italian side, the smoke surged towards France. The Italian control center switched on the fans to blow the smoke through, but instead of clearing it, they simply fed oxygen to the fire, making it burn hotter and faster. The tunnel's refit has adopted an innovative system, which it's hoped will prevent history ever repeating itself. 116 new ceiling fans have been fitted along the tunnel. The fans maintain an area where wind speed is 0, the point depicted by the yellow line. This 0 wind speed zone can be manipulated remotely to control the movement of smoke. In the event of a fire, the fans direct the still zone to the area of the blaze, allowing smoke and fumes to be removed through extraction vents by powerful ventilators. At the same time, the new ventilation system brings fresh air into the tunnel.
In this very large technical room, you have two kinds of turbines. You have on my right hand, you have the blue one in place to pump the fresh air from outside and to push it inside the tunnel. So fresh air is very cold and they don't need special protection. But here you have the red turbines. These turbines are protected. They are here to extract the smoke and extract the hot air in case of fire inside the tunnel.
With the smoke under control, the rebuild addresses the provision for refuge and escape. The old fire rooms along the edge of the tunnel were death traps, quite unable to cope with the ferocity of a high-intensity blaze. The escape system has been entirely rebuilt, with new safety shelters capable of withstanding heat up to 1,000 degrees centigrade for 4 hours.
Okay, I'm entering now in the safety shelter. The safety shelter is a place where you are completely safe. The only thing you have to do is to wait for further instructions. And the further instruction will come through this video system. And through this video system, I'm able to enter in contact with the operator. I push.
Hello?
Bonjour. We are in the shelter number 16.
Yes, you are there and now you wait there.
Okay.
Our rescue team will be arriving in 2 minutes.
Okay. So the operator said me that I have to wait here for the rescue team and the rescue team will come through this door.
The key innovation in the new rooms is that this time they're connected to an escape tunnel that leads to the French and Italian exits.
To the escape corridor and you follow me. Normally, the rescue team will open the door and we are now under the way and you have Italy here and France here.
The new Mont Blanc tunnel is an old structure that has been rebuilt, but it will never be risk-free.
We will never say that. We did the maximum to avoid terrible consequences to an event. But nobody can say that we will never have an event in the tunnel.
180 kilometers away in Switzerland, the brand new Lochberg tunnel has also learned lessons from the Mont Blanc road tunnel disaster. Opened in 2007, it's a dual-bore rail tunnel. The escape system here is on a grand scale, capable of dealing with 1,500 passengers. Lochberg is the third longest tunnel in the world at 34.6 kilometers long, 3 times the length of the Mont Blanc tunnel. To cope with the size, here the ventilation system is colossal, built to deal with a high-power fire reaching 1,000 degrees centigrade.
So we're here in the ventilation center of the Lötschberg base tunnel. There are two such centers, one here, one 50 kilometers north, with two ventilators. Each of them can pull 200 cubic meters of fresh air into the tunnel system. This ventilation system is crucial for the security in the Lötschberg tunnel. It's used to take out polluted air in case of a fire from the railway tunnel tubes and takes it outside. Here we see how fresh air from outside is brought through these noise-reducing walls into the ventilator and is pushed with force into the tunnel. It's now running only at 25% of its capacity. In case of an emergency, if it would run full speed, it would burst our ears. But now it's quite quiet, that's why we can still talk.
Lötschberg also addresses the need to get the emergency services in as quickly as possible. At Mont Blanc, the firefighters were obstructed by the heat, smoke and darkness. Here, the system boasts the ultimate in early response, the fire train.
Also bei einem Alarm, Brandalarm, wird es 5-6 Minuten gehen mit beiden Wasserwerfern. Und dann lassen wir knapp bei 5000 Liter raus und haben 50 Kubik dabei, also das ist relativ schnell, wäre es leer.
The train isn't just about fighting fires, it's also a mobile hospital.
Der Zug zu trennen in Löscheinheit und Rettungseinheit. Mit der Rettungseinheit können wir einen Shuttle-Betrieb machen. Also das heisst, wir können Leute aus einem Gefahrenbereich rausbringen.
But even this system has limitations. In the most intense heat, above 1000 degrees centigrade, there's little even the most rapid response team can do.
Und dort ist das Limit ganz sicher Hauptaugenmerk auf den Menschen. Was kann der Feuerwehrmann oder Frau, was können sie noch schaffen? Können sie noch schaffen oder gar nicht mehr? Und dort ist die Limite. Dort muss man dann auch den Mut haben und sagen, es ist nicht mehr bekämpfbar und den Rückzug nehmen.
In Turkey, the Marmaray project has taken the lessons from Mont Blanc to the extreme. Although this tunnel will be relatively short, just 1.5 kilometers between the stations on either side of the Bosphorus, its ventilation system will be the most powerful in the world. And this is where they're going to put it. The Cercagie Deep Station. This massive ventilation chamber is only a small part of the huge station complex under construction. Chief Engineer Melir Babur is in charge of the design of the ventilation systems.
Okay, we are at the west ventilation shaft of Cercagie station. The total shaft length is around 200 feet.
As always, the key to any ventilation system is to have control over the smoke in the tunnel.
And we want the smoke to move in a certain direction so we can have the passengers evacuate in the other direction. This is the main purpose, okay? There are going to be about 7 different levels, equipment levels, and each level will contain different equipment. Most of them are dealing with the emergencies, like tunnel ventilation funds will deal with emergency situation. The main purpose here is to reduce the risk of fire, and when the fire starts in that unfortunate case, to put aside the adverse effect of the fire.
As in Lötschberg, there will be ventilation plants at each end of the tunnel, one in Europe, the other in Asia, with one set of fans sucking air out, the other pushing it through. The lessons of the Mont Blanc disaster were swiftly learnt and rapidly implemented. But despite this, only 2 years later, another Alpine tunnel disaster was to horrify Europe. The Gotthard road tunnel connects Switzerland and Italy. When it opened in 1980, unlike the Mont Blanc road tunnel, the Gotthard tunnel was already equipped with a state-of-the-art fire detection and evacuation system and was considered the safest in Europe. But refuge cells constructed every 250 metres of its 16.4 kilometre length and an advanced tunnel ventilation system weren't enough to prevent the tragedy to come. On October the 24th, 2001, two lorries travelling in opposite directions collided 1.5 kilometres from the Italian entrance. A ruptured fuel tank immediately ignited. Vehicles travelling in both directions on either side ground to a halt. Urs Gerber was caught in the jam.
Coincé, donc j'ai arrêté le moteur. Je suis sorti et puis je suis allé contre la mur, donc direction nord. Et là, tout d'un coup, c'était sombre.
As the fire took hold, wheels exploded in the heat and toxic smoke filled the tunnel.
J'entendais des petites cris et puis des petites explosions, mais à ce moment-là, c'était comme, il faut dire, comme un rêve. Alors je voulais pas mourir, et puis pourtant je sentais que j'arrive plus à respirer comme il faut. Donc.
Gerber and 4 other drivers couldn't find the escape room, and the air was running out. They were trapped.
Pas plus, donc, parce que c'était seulement la volonté de survivre qui m'a tenu en vie.
By chance, one of the group managed to locate an exit.
Il a ouvert la porte, et puis à ce moment-là, c'était clair, et puis on était sauvés, on peut dire. Hein.
Not all the people caught in the tunnel were as lucky as Gerber. Walter Steiner was tunnel controller on the day of the fire.
Es gibt Chauffeure, die sind mit dem Rauch geflüchtet und konnten den Schutzraum noch erreichen. Und das haben aber nicht alle geschafft, sondern sie haben den Eingang zum Teil nicht mehr gefunden oder sind zum Teil im Fahrzeug geblieben. Sie sind alle in den ersten 10 Minuten erstickt aufgrund der toxischen Rauchgase.
In all, 11 lives were lost. After the tragedy, steps were taken to improve the emergency lighting system, making it easier to find your way through dense black smoke. But shocked that lives were lost, despite the state-of-the-art systems already in place, designers now focus their attention on trying to prevent accidents happening in the first place. One innovation was to monitor and control the volume of heavy goods vehicles entering the tunnel at any one time. An automated system was put in place to drip feed a maximum of 3 trucks per minute into the tunnel. Using a traffic information collector, operators not only monitor the speed of vehicles, they ensure that vehicles are kept apart.
Nach diesem Unfall hat man versucht, mit einem System die Lastwagen auseinanderzunehmen, größere Abstände zu bilden.
Before the accident in 2001, there were 45 vehicle fires in the tunnel every year.
Heute mit dem System sind es nur noch 10. Also 10 pro Jahr.
The Gotthard team went a step further. They wanted to solve the problem of how to prevent spontaneous combustion of the sort that had caused the catastrophic fire at Mont Blanc. At the Gotthard tunnel, a new technology is being introduced that will combine 3-dimensional thermal imaging cameras with the traffic control system.
This object you see is car transporter. You can measure this object, you can do everything with it. This is the base for all our applications.
The next step is to take a thermal scan and drip it over the 3D object.
We see here that it's a hot spot here at the end of the vehicle. Whenever we see, okay, that's the one which we think it's too hot, and then the operator has to react, and he has to go on and has to pick it up out of the traffic. In the Gotthard Tunnel, there are multiple fires every year. We can reduce this number of fires by 80%. Then we have a huge advantage.
Through traffic control and early fire detection, it's believed that the Gotthard Tunnel will be less exposed to another killer fire. In recent years, many of the big tunnel fires resulting in loss of life have been in a road tunnel. Vehicles, and especially large vehicles, trucks and lorries, are travelling bombs, primed with fuel, sometimes carrying highly volatile cargoes, subject to spontaneous combustion and vulnerable to driver error. One answer to some of these issues is to completely replace road with rail. The new Marmaray project in Turkey is a rail tunnel. All freight will be carried by train, not by truck. 2 separate tunnels, one in each direction, prevent the risk of the trains colliding. And by eliminating heavy goods vehicles altogether, the tunnel's designers have taken on the lessons of previous disasters. But even train tunnels can be plunged into chaos by major accidents. In 1996, the Channel Tunnel that connects England and France revealed a frightening weakness in its design. It was the most advanced rail tunnel of its type, built as 2 tubes with a separate rescue tunnel and crossings at every 300 metres. It was thought to be the safest tunnel in the world. It runs through the chalk seabed that lies under the English Channel, connecting England and France. At 9:48 p.m. on the 18th of September, a Eurotunnel cargo train entered the Channel Tunnel at Sangatte, near Calais, northern France. On one of the trucks in the cargo section of the train, a fire was smouldering. The fire spread to the train, and 19 kilometres inside the tunnel, it suddenly stalled. The blaze was soon out of control. In the smoke-filled darkness, the train's 33 passengers and crew were led towards the safety tunnel by the fire services. It was a narrow escape.
We couldn't see because the smoke was getting into our eyes.
I thought I was going to die, I really did. I was laying on the floor, everything was going, lightheaded. I thought I'm going to die here.
The passengers were safely evacuated, but the fire couldn't be controlled. It had already reached critical temperatures over 1,000 degrees centigrade. The concrete tunnel lining began to spoil, falling away in huge chunks. At the heart of the fire, the lining was almost completely lost. Luckily, the tunnel was running through a dry part of the seabed. If there had been water on the other side of the lining, there would have been a catastrophic flood. Professor Gabriel Alexander Coury of Imperial College London has studied the 96 Channel Tunnel fire.
Half the section was destroyed, and in some parts, the spalling took place all over the section, right up to the ground. Now, that is structural damage. 500 meters of the section was damaged, of which 50 was serious, and that is in terms of the explosive spalling of concrete.
The tunnel was lined with high-strength concrete, where additives like fly ash create stronger chemical bonds in the concrete mixture. At the same time, the amount of water is reduced, which also increases strength. But in the Channel Tunnel fire, even this small amount of water became a hazard, turning to steam in the intense heat. The water pressure rose as high as 100 times atmospheric pressure.
The steam pressures will build up faster than they can be diffused, and there is a risk of an explosion taking place.
In the high temperatures, the lining of the tunnel literally blew itself apart.
And the firefighters in 1996, they said that the concrete was falling on them like shrapnel.
After the 1996 fire, Eurotunnel repaired the damage using the same high-strength concrete lining. But they upgraded their fire and rescue services in the tunnel, a strategy that withstood the test of another serious fire in 2008. Even though this type of concrete is now known to explode in intense heat, it's still in use in tunnels across the world. Some tunnels, like the Loschberg Base Tunnel, are immune to the threat of collapse. Because of this, the Swiss Alps, made of hard granite.
We have a stable rock structure, so there's no risk of a breakdown of the tunnel. Even if this concrete here would burn down or break, the tunnel would not break down completely. So this is a risk that we can almost exclude.
But 2,000 kilometers away in Istanbul, the Marmaray Tunnel doesn't have the protection of granite. It's lined with high-strength concrete, but lessons from the Channel Tunnel fire have been taken on board.
In the history, there are that sort of accidents which happened both in the highway tunnels and also the railway tunnels. And Channel Tunnel fire is one of the most serious examples in the past. So based on that, of course, we took lessons.
The concrete used to line the Marmaray Tunnel is protected with a fire insulation layer.
And there will be an application of fire insulation material depending on the ground conditions, the rock quality, whether we are in the fracture zone, the groundwater level, because we have to eliminate catastrophic failure and we have to prevent flooding.
The tunnel boring machine is a 150-metre-long complex that removes the rock debris from the drilling face at the leading edge of the tunnel.
We are at the end of that TBM5. We have, as I have mentioned, excavated 2 kilometers until now. And you may see that cutter head, which is the main part of the TBM machine you see there. These are the pistons which are located at the periphery of that cutter head, which has on the order of 75,000 kilonewton thrust force, which pushes the ground like that. So this machine is manufactured specifically for Marmaray project, considering all the soil conditions, the strength of the rock, etc. We will connect to the IMT, the element number 11 at the Asian site. So the IMT element and TBM will connect to IMT. We will do all these water insulation works and the inner concreting works, and at the end we will be able to have the full tunnels under the Marmaray project.
Fire is not the only threat to the structure. This huge tunnelling project is only 10 miles from the North Anatolian fault line. For Deputy Project Manager Hussein Belkaya, structural failure and flooding of the tunnel due to earthquakes is a very real hazard.
The occurrence of a big-scale earthquake in the next coming 30 years in Istanbul is 62%. This is really very high percent.
Like the Channel Tunnel, the Marmaray Tunnel runs through the seabed. Flooding is a real and potentially catastrophic risk. It's a threat that was brought vividly to light 2 years into construction. At one of the stations that will link the tunnel system together, they unveiled the remains of the ancient harbour of Byzantine Constantinople. Complete with 32 warships, this was one of the greatest archaeological discoveries in Turkey's history. For archaeologist Doğan Perinçek, the dig also offered up an environmental warning from history.
This excavation area has many chapters. And within this marshy sediments, we have some sediments related to flooding. What caused this? What's the reason of this?
For Doğan, the key to unlocking the mystery lay in the historical records of Byzantium. In the 6th century, there had been 3 major earthquakes, and the new evidence of flooding pointed to one of earthquakes' lethal side effects: tsunami. 1,400 years ago, a giant wave had devastated the port.
Earthquake during the 6th century and related to tsunami destroyed many things in the region. And the part of the harbor destroyed, and also wall of the city destroyed. And same tsunami destroyed the piers located within the harbor.
Tsunami modelling suggests the wave was between 6 and 8 metres high and had struck the port right where a crucial element of the tunnel was now being planned.
They are going to build a station here. And entrance of this station should be 6 or 8 meters higher than present-day sea level. Otherwise, will be disaster.
The tunnel's designers took their history lesson to heart and raised the height of the station entrances to protect the build against a future tsunami.
We have to be very cautious and we have to take lesson from the past.
In a dry dock 40 kilometres from the Bosphorus, the 11 segments that will connect east and west are being constructed. A single segment weighs 18,000 tonnes, and at around 150 metres, each one is longer than a football field. The tunnel is itself designed to absorb the impact of an underwater earthquake, measuring up to 7.5 on the Richter scale.
Şu anda üzerinde bulunduğumuz tüp elemanı, boğaz tüp geçiş elemanlarının içerisinde sonuncusudur. En sonuncusu bu eleman, 11 numara. Boğazda batırılan bu parçalar, boğazda şu elemanlar aracılığıyla, şu contalar aracılığıyla birbirine bağlanıyor. Birbirine sızdırmaz hale geliyor. Ve ortaya çıkan bu 1400 metrelik tünel hattının sismik jointleri var giriş ve son uçlarında. Dolayısıyla bütün bu sistem depremde yarım metre hareket edecek şekilde inşa edilmiş olmaktadır.
Inside this segment, Adnan makes some last-minute checks before it's submerged. It will be floated into position above the drop location, where a series of ballast tanks will be filled to sink it to the seabed. For Adnan and his team, this isn't just a piece of engineering, it's an historic moment.
Böylece İstanbul Boğazı'nın altından ilk kez bu büyüklükte bir tünel, bir geçiş sağlanmış oldu. Bu belki 200-250 yıldır insanımızın bir hayaliydi. Bu gerçekleşmiş oldu. Tam bu nokta işte, bu tüneli Avrupa tarafına bağlayan ucudur.
In addition to seismic joints, the tunnel designers have ensured that the tunnel will not be damaged by liquefaction. Geologist Dr. Orhan Simcek has identified the problem areas.
This is a geological longitudinal profile of the Bosphorus channel along the immersed tube alignment. This is sea level, this is seabed level, this is rockhead level, and this is immersed tube alignment. The yellow color, soft clay material, call it golden horn clay. Towards east, Üsküdar side, immersed tube foundation is made up of sandy material. During high seismic event, there is a risk of liquefaction potential.
The Asian side of the tunnel lies in sandy soil. An earthquake would be disastrous.
It is estimated that fault rupture in the same segment happen between 200 and 300 years, recycling. So the last major earthquake in the center of the Marmara Sea happened in 1776. So you come to the States. So it is a high probability to have a major earthquake during the service life of this project.
The solution is simple: to surround the tunnel in a coarse gravel lining. The dredging vessel is busy day and night. The gravel will insulate the tunnel from seismic shocks.
In order to avoid the liquefaction risk in the sandy soil, you have to drain the soil. To drain the soil around the tunnels, immersed tunnels, coarse-grained crushed stone is required to have voids to release the pore water pressure during the seismic event.
When a serious earthquake eventually strikes, the large voids in the coarse gravel cladding around the tunnel will release the pressure build-up, protecting the structure. Simple, but effective.
This relaxation of the pore water pressure will prevent damage from the earthquake.
The Marmaray project is in the final stages of its construction. Many of its fundamental design features will have been informed by past disasters. Post the Channel Tunnel collapse, the Marmaray project will be protected from fire by a layer of thermal insulation. From the Mont Blanc fire comes the most powerful ventilation system in the world to control smoke. And the archaeological lessons of history bring a system of seismic joints to resist the effects of an earthquake. Above all, the Marmaray System's engineers are determined to eliminate truck driver error. Under the Bosphorus, 2 parallel rail tunnels will carry only high-speed trains. Truck shuttle trains will eventually pass through the tunnel, but trucks with flammable loads have to cross the Bosphorus by ferry. Despite all the challenges to construction, the tunnel project is back on track and due to open in 2012. 10 of the 11 tunnel segments have now been laid. At a depth of 58 metres, the tunnel has to be able to withstand 6 times the atmospheric pressure at sea level. For the immersed tunnel project manager, Hideki Sakaide, the tunnel is a new silk route between Europe and Asia.
Then we are now walking towards the European side. So we can say now we are walking in the new Silk Road.
The East and West are almost connected. Tunnels are on the brink of a new era. In many countries, a new movement has begun that aims to use tunnel technology, not just to connect people and places, but to construct whole new worlds underground. Amsterdam in Holland is one city fighting a very modern battle for more space. The city is in crisis. If cars are prevented from entering the historic city centre, the local economy will die. If the crowding continues, the city could become a polluted wasteland. Civil engineer Bas Obladen has a vested interest in solving the problem.
I was born in Amsterdam, and when I was young, that's so 60 years ago, it was a very nice town to be and to live there, and the quality of life was also very nice in those days. And say 8 years ago or so, I went with my son. I said, I show you the places where your father have been born and where he lived. I was shocked about what I saw. Everywhere there were cars and bikes, and it was terrible in my opinion.
Baz's vision is to remove cars from the roads and canal sides. And using tunnelling technology, take them below ground.
If the cars are, say, under the ground at the moment, then you get fresh air above the ground. So people are living longer, the quality of life is very nice. And alongside the canals, there are no cars.
The idea is to funnel traffic from the ring road into an underground network of tunnels. Amsterdam's canals provide the blueprint.
We have a lot of canals in Amsterdam, so I'm using the canals for a road under the canals from the ring road to the underground system.
But tunnelling in Amsterdam is technically challenging.
The main problems in Amsterdam is, of course, the water level.
The engineers on the current north-south tunnel dig under Amsterdam are developing techniques that will help realise the new project.
Our main challenge in this area is the softness of the soil. We have to try to maintain a stable environment for the drill to go through. So what we do is we drill 90-meter long poles that will be used for a brine solution that will cool down the entire soil and thus creating a frozen, like a permafrost layer through the total width of the 2 drilling machines.
As the technology has developed, so has the ambition.
The idea is not to make tunnels to a destination and then connect different destinations. So we say if you build a connection, why not make it a useful space? So it's all about really making a very big space. It's like the doubling of the floor space which is in the center of Amsterdam.
The design would not only provide much-needed parking, massive underground spaces would house cinemas, squash courts, and even swimming pools. Those behind the Amsterdam project are conscious that whatever the space is used for, safety lessons from past tunnel disasters still have to be applied.
For the fire safety, we are really looking into the possibilities of compartmentation and that you are always within a reasonable amount to walk to a safe place. So if something happens in your vicinity, you can hold your breath and How many meters can I walk? Well, there would be a door. That is basically where we start from. And there are now materials which can really keep the fire on the other side of the doors.
For now, the Amsterdam dream of building urban spaces below the city streets is in the early planning stages. But in Turkey, the Marmaray Tunnel project is fast becoming a reality.
It is always difficult to construct a mega project in an urban, densely populated area. But once it is in operation, Marmaray project will save a lot of travel time and make the lives of more than 1 million passengers per day more comfortable.
Throughout its lifetime, the Marmaray Tunnel will face a double jeopardy of fire and seismic shock. But with the legacy of past tunnel disasters designed into its very fabric, it's being built to confront and overcome whatever challenges the future might bring. For thousands of years, ships have allowed man to travel the globe, crossing the vast emptiness of the oceans. The rewards for these journeys have been huge. So is the cost when things go wrong.
It's incredible to see what happened. People are drowning in the ice-cold water.
But every disaster has radically changed the design of the ships that followed.
Every single decade, we learn more and more after every casualty.
Designers strive to make their ships stronger and safer by learning from the tough lessons of the past. From classic cruise ships to cutting-edge designs, modern vessels are literally built from disaster. Disaster at sea can be a terrifying and deadly experience. Often miles from assistance of any kind, passengers and crew have only themselves and their ship to rely on. The ocean is an unforgiving environment where there are no second chances. In 1994, 852 people died after the car ferry Estonia sank in the Baltic Sea. In 1990, a fire on board the Scandinavian Star killed 158 passengers and crew. And most famously in 1912, over 1,500 people perished in the icy wastes of the North Atlantic after the Titanic hit an iceberg. These and other tragedies highlight three of the primary risks faced by passenger vessels: collision, capsize, and fire. The designers of all modern passenger ships use every tool at their disposal to limit the risk of these dangers. And this can be seen clearly in Italy, where one of the most high-tech cruise ships ever built is nearing completion. This is Ruby Princess. $500 million, 290 meters long, and over 116,000 gross tons. Built to cruise the Caribbean, it's taken just 14 months to get the ship to this stage. Giorgio Gomiero is the man responsible for this cutting-edge project.
We are going something like 45 meters, 15 decks when we come at the top. Ciao, buongiorno. Ciao. Okay, we are on board Ruby Princess. This is our latest ship that we are going to deliver in a few months. We built the ship piece by piece. This is definitely an handmade product.
With cabins for 4,800 passengers and crew over 19 decks, this ship will be a complete floating city with every conceivable passenger facility built in. There are 5 swimming pools, 7 restaurants, and even a wedding chapel.
Watch your step. This is a bar. And it is a covered area. We have an hamburger bar, we have another bar over there. Of course, this is a public space. It's a passenger ship. There is quite a lot of space to have fun, to have a drink, to take a rest, to have a swim.
Incorporated into this vast vessel are the latest advances in ship construction and safety systems.
When you start with the project, you have also to take in mind all the safety of the ship. And you have to build the ship also taking all these constraints. And you have to respect all these constraints till the beginning.
The process starts with 19,000 tons of high-quality steel plate. This is made into precise shapes by a plasma cutter, and then welded to form sections, which piece together to make up the ship.
So we build the ship like a Lego, actually. The ship is built in the dry dock. We have these big sections that are taken in dry dock, they are put together. One big section is going on board. All the sections should go on like this, and the section is then welded and outfitted.
This huge structure is an incredible feat of maritime engineering, built to withstand the awesome power of the sea. Modern passenger shipping is now one of the safest forms of transport on Earth. But it wasn't always that way. April the 7th, 1990. The passenger ferry Scandinavian Star was travelling between Norway and Denmark with 482 people on board. In the early hours of the morning, a fire broke out in an unused accommodation area. The fire gained strength and rapidly spread throughout the ship, producing clouds of thick, toxic smoke in the corridors. Desperate for oxygen, the passengers searched for ways out.
I heard this noise from the fire, and I saw all the smoke coming out from every open door. I remember that it was so much smoke, and it was like a very huge waterfall of smoke. Then I understood that this is a great disaster. This is terrible. People are dying here now.
At 3:20 a.m., with the fire out of control, the captain gave the order to abandon ship. 3.5 hours after the blaze broke out, rescue helicopters reached the vessel. Firefighters were confronted with a horrifying scene. 158 people were found dead. Trapped in cabins and corridors, many of them hadn't even made it outside to the deck. After evacuating the survivors, the smouldering ship was towed to Sweden, where it took firefighters a further 2 days to extinguish the blaze. The fire was later thought to be caused by arson, but however it started, the results were catastrophic. The ship had serious shortcomings that contributed to the disaster. No smoke detectors or sprinklers in the passenger quarters, malfunctioning fire doors, inaudible fire alarms. But these factors alone did not explain why so many died. During the subsequent investigation, 2 shocking discoveries were made. The first was that many passengers simply could not find their way to the emergency exits. The second was that the fire spread incredibly quickly.
The development of the fire came as more or less as a surprise to our investigators. The fire was much more intense and rapidly intense than we expected.
The investigation found a number of causes for the rapid spread of the fire. One was that large parts of the ship's interior had been coated with a highly flammable plastic laminate. But this plastic didn't just intensify and spread the fire, it also gave off highly toxic fumes.
Hydrogen cyanide is a very toxic gas, very dangerous gas, and this is a gas that with low concentrations also could kill people within a few minutes or even a minute. And it's actually the same gas as Hitler used during the war, killing the Jews in the gas chambers.
The hydrogen cyanide given off by the plastic laminate was the direct cause of many of the deaths. This could not be allowed to happen again. All passenger ships built today must adhere to strict rules regarding the type of materials used in their construction. Virtually all the material must be non-flammable and non-toxic. Antonio Bartolini is in charge of fitting out the passenger areas on Ruby Princess.
This is the main theater of the ship, which provides seating for over 800 people. This wall looks like wood. It's actually not wood, but is a thin veneer applied on a not flammable material. Also, the carpet is not flammable, and is made in a way that the smoke is not toxic.
Flammable plastic laminates like those used on the Scandinavian Star have been outlawed for use on passenger ships. But another reason for the rapid spread of the fire was more complex, and it concerned information.
Knowledge is everything, and information is critical in an emergency.
The accommodation areas weren't fitted with automatic smoke detectors connected to the bridge, so the crew didn't know that the fire had started on deck 3. So not all of the fire doors in that area were closed, and the fire quickly spread around the ship. The tragedy on the Scandinavian Star would become the catalyst for a new generation of high-tech safety monitoring systems. These are now mandatory on passenger ships, and the one being fitted on board Ruby Princess is state-of-the-art.
All these cables are coming through from all the detection systems on board, and they are passing into the safety management system. These systems makes the operator to be able to monitor the ship for fire detection system, water mist heads, and fire doors, watertight doors, so you can always monitor your ship.
The wiring matrix for the ship uses around 2,500 kilometers of cable.
So these cables are for safety systems and all the automations. The cables are on segregated cable trays in order not to interfere the signal cables from the power cables.
The safety management system has sensors in every area of the ship, so it can provide an instant snapshot of an unfolding emergency.
It's sort of remote eyes and ears of the operator. So it's sort of like having a big brother looking over you all the time, all over the ship.
This is one of the benefits of our age. We have technology. We know not just that one fire detector is going off, that multiple fire detectors are going off. Why is that important? It tells the officer on the bridge, this smoke is progressing. This is not a detector failure. Something's going on down there, and you need to take action.
Sensors are constantly vigilant, checking for smoke, temperature changes, and flooding. Before Ruby Princess is handed over to the owners, 6,000 smoke detectors and heat sensors across the whole ship must be tested, a 6-month job.
So now he will activate the smoke detector and we will verify the actual alarm. Pre-warning, no? Prima. The alarm has been activated and you see that this was the peak of the smoke detection.
If nothing was done about this alarm, the safety management system would take over. Fire dampers would shut, cutting off the air supply to the fire.
Fans have gone from the red color to green color, so from running condition to the stopped condition. We've just stopped the air supply to that part of the ship.
The water mist system would then activate. This is the latest in sprinklers. Pressurized to 150 bar, the water is sprayed as tiny droplets.
It's a matter of minutes extinguishing fire.
Conventional sprinklers are problematic on ships as they allow large amounts of water to collect, which could cause destabilization or even sinking. The advantage of the water mist system is that it can extinguish a fire using very little water. And it's now widely used on many types of ship. The appalling events on the Scandinavian Star had far-reaching effects on the regulations regarding materials and monitoring systems. But the inquiry also revealed a much more fundamental problem with the ship. The evacuation routes were poorly thought out and managed. Many dead ends and twists and turns trapped disoriented people in the thick smoke.
We could see a lot of people dying just aside a fire exit. I think 12 people were found in a corridor with a dead end. And if you go back 1.5 meters from the dead end, there was a fire exit just to the outside, to the open, to the deck. and 12 people were found on the floor, dead.
In response to disasters like the Scandinavian Star, evacuation planning is now considered at the earliest stages of a ship's design. On Ruby Princess and other cruise ships, one of the primary aims is to make sure there's always a way out.
You have to avoid the dead end, and there is a fire here. Naturally, you are psychologically, you try to avoid the fire, so you escape in the opposite direction. If you want to escape in the opposite direction and there is no any other exit, that is a dead-end corridor, and it can happen that the people are trapped inside. Nowadays, all the corridor is designed in such a way that you can always find a different means of escape, bringing you in the same state or the same primary route. That is the modern way to design the escape route of a passenger vessel.
During an evacuation, time is critical. To ensure that passengers can escape fast enough, the evacuation routes are tested with computer modeling.
According to the rules, we have 30 minutes for the assembly, for the mastering time, and 30 minutes for the embarkation and abandon ship process.
All the lifeboats are simulated by these areas here. And so we have from the deck of the ship, where the assembly stations are, you can see all people moving and moving from the public spaces into the assigned area that correspond to the lifeboats. So it is possible to check physically with a sample of travel time and speed of the different occupants, how long does it take for the whole population to reach safely the embarkation points?
On this ship, using the specific tools and the software simulation, we can demonstrate that all the occupants can safely be inside the lifeboats in approximately 20 minutes, so having a large margin in comparison with the rules.
The journey towards safer shipping has been a long one, and the disaster which advanced it more than any other is perhaps the most famous shipping tragedy of all time, the sinking of the Titanic. On the 14th of April 1912, with over 2,200 people on board, the Titanic was on its maiden voyage across the Atlantic to New York. She was the biggest passenger steamship of the day. In fact, the largest moving object ever created by mankind. Incredible luxury, combined with great speed, Titanic incorporated two major safety factors in her design. The first was a double-bottom hull, which protects a ship if it hits an underwater obstruction. The second were her compartments, which subdivide the interior of a ship to stop the spread of flooding. These and other design features gave the ship a reputation for safety and inspired great confidence in her passengers and crew. Some even called her unsinkable. But that night, they were proven wrong. Just after 11:40 p.m., the gigantic ship struck an iceberg. She was at least 560 kilometers from the nearest land. As the iceberg scraped down the starboard side of the ship, it caused massive damage.
This damage went for over 90 meters, and it opened up a third of its length of the starboard side.
The ship could have been protected by her double-bottom hull, but the iceberg had damaged the sides of the ship, above the level of the double bottom. As a result, vast amounts of icy water flooded into Titanic. In this situation, her other design feature, compartments, should have limited the amount of water that could enter the ship. But there was a problem. The damage had compromised not one, but 5 of Titanic's compartments, an impossible breach which would sink any vessel. What became critical now was whether she would stay afloat long enough for a rescue vessel to reach the scene. One aspect of the ship's design proved disastrous. As the damaged and flooding bows sank lower into the sea, the rising water reached the top of the bulkheads that formed the compartments, but these weren't completely sealed to the deck above.
The compartments themselves were not fully watertight. They were open at the top. So what happens is, as water goes into one compartment, it weighs down the ship, and if the ship goes down far enough, water will start to pour in to the next compartment. Because it breached 5 compartments, this cascading effect of flooding could not be stopped on the Titanic, and it went down in 2.5 hours.
When the steamship Carpathia eventually arrived at the scene, the Titanic had already gone down, and the majority of her passengers were dead. Over 1,500 people died in the disaster. Many factors are thought to have contributed. The quality of the rivets used in her hull, her high speed in a known iceberg area. And shipbuilders have learnt many lessons from this legendary shipping tragedy. One of Titanic's design features, the double-bottom hull, is still in use. It's still one of the best ways of protecting a ship from damage caused by a collision with an underwater obstruction, and has saved numerous ships from sinking. The reserve inner hull prevents water flooding into the ship. On Ruby Princess, this double bottom is 1.8 meters deep. To get a proper look at the hull, the ship would have to be lifted out of the water and literally cut in half. But just a few hundred meters away from Ruby Princess, there's a new cruise ship at a much earlier stage of her construction.
You can see here actually a complete section of the ship, and you can see how the ship is built.
This gives unprecedented access to view the double bottom.
The first level is the level of the double bottom. The double bottom is 1.8 meters from the keel, and is there in order to give a safety in case of grounding of the ship. On board the passenger ships is actually specified to have a continuous double bottom from forward to aft.
Underneath, the scale and strength of this vast vessel becomes apparent.
Pay attention, because there are a lot of workers. This is the shipyard.
The level of the double bottom is marked on the outside of the ship.
That sign, the T, the sign T, indicates the placement of the double bottom, okay? The double bottom in this case is more or less 2 meters.
Like the double bottom hull, Titanic's other design feature, compartments, are also still used on modern ships, but with several important changes. One of the biggest improvements was to make the compartments absolutely watertight. This is the Fram. Right now, this brand new cruise ship is sailing near Greenland. But this ship isn't trying to avoid icebergs like Titanic. She's actively looking for them. Her passengers want to see these huge ice mountains close up. The Fram has been designed specifically for this type of cruising. Areas of the hull at risk of collision damage have extra thick plating, and the stem at the front of the ship is made out of an immensely strong single piece of steel. But it's her watertight compartments that are the biggest safety factor.
Outside here is seawater. My head now is about 2 or 2.5 meters below water level.
The bulkheads forming the compartments are welded on all sides to the decks and other bulkheads around them, making them completely watertight.
This wall here is a watertight bulkhead. The bulkhead is attached to the deck above. It starts in the bottom of the ship and goes all the way up to deck 3. No water can penetrate through this bulkhead.
Anywhere that pipes or wires pass through the bulkheads, there are rubber seals.
We have bulkhead penetrations that are waterproof. The pipes are sealed into these penetrations. There's rubber, and it's tightened together, so it's impossible for water to penetrate. I guess it's kind of nice if you don't want the ship to sink.
Another lesson learned about compartments after Titanic was that the more compartments a ship has, the less likely it is to sink after a collision.
Today, passenger ships are very highly subdivided, so simply having damage along the side of the ship doesn't mean a whole compartment running the entire width of the ship is going to flood. That flooding may not make it that far because the compartment is so subdivided.
Here on Ruby Princess, there are 19 compartments compared to Titanic's 16. Most of the bulkheads that form them have doors to allow people to move around inside the ship. These doors must be watertight and on Ruby Princess can be closed remotely or locally.
If a compartment is flooding, this sensor will detect the flooding, the air level on the bilge, and you will get an alarm in the alarm log. And if they cannot stop the flooding, they will communicate to shut down the compartment, close the watertight doors, and permit the compartment to flood safely.
The lessons learned from Titanic are incorporated into virtually every modern ship afloat. But there was one aspect of the disaster that had a bigger effect on safety at sea than any other. It seems unbelievable, but on Titanic, there were only enough lifeboats for just over half those on board.
Because of the Titanic, today the Safety of Life at Sea Convention specifies that 100% of the people on board must be provided with a lifeboat seat. Therefore, you have a 100% capacity, and that requirement has been there since 1914.
For ships like the Fram that operate in remote areas, access to lifeboats is of paramount importance.
We are ready to release lifeboat number 4.
Lower lifeboat number 4 when you're ready.
Okay, you can release. Well, now we are lowering the lifeboat down to embarking position. So we make it ready for the passenger to embark. And then we will keep on launching it down to sea level. When we are a long way from the coastline and also a long way from other ships, it's of course important to have the equipment that will ensure us to survive as long time as possible. So to have covered lifeboats with food and equipment that you need to survive for a long time, that is absolutely important for us. 150 people can fit in this lifeboat. Seems incredible, but you sit very, very close to each other, and that can also be a plus because of the temperature. Okay, then you can enter the boat. Today is just a drill on how we will do it in an emergency situation. Of course, we hope that we never have to do this in a real situation. The lifeboat is more than good enough to spend time in, but we like it better when we could spend it on fun.
For the passengers of Titanic that did make it to the lifeboats, the ordeal was far from over. They had few provisions and minimal shelter. Many of them died of exposure because the boats were open to the freezing weather. Many lifeboats today are enclosed to keep the occupants out of the wind and spray and have advanced features to aid survival.
In this locker we have fresh water for everyone who's in here in the case of an emergency. And there's half a liter for every person every day, 3 days. Inside this locker is a maintenance sheet for the engine. We have drift anchors. We have also food in these boxes. And we have thermal protecting suit, keeps us warm. This boat is basically a life support system in case of emergency.
Lifeboat provision on modern passenger vessels means abandoning ship is a far more survivable operation, and this is directly because of Titanic. But collision is still one of the primary causes of disaster at sea, and although modern mariners have many tools at their disposal to reduce the risks, sometimes they need a little extra help, particularly when entering or leaving port. This is the Solent, one of the busiest sea areas in the world. Every day, thousands of vessels pass through, come rain, shine, or thick fog.
Yeah, Team Southampton, VTS, good afternoon, sir.
In 1 hour will be in the pilot position on North Star.
White Sea VTS, it's a candle.
Roger, sir. 1345 pilot launch will be with you.
Because there are so many vessels in close proximity, the chances of collision are high. So the 5 staff in this room monitor the area, making sure the vessels stay clear of each other.
This is the operations room in the VTS Centre for the Port of Southampton. It's not exactly the same as air traffic control in that they give much more discrete or distinct orders to aircraft to follow particular distinct flight paths and flight levels. We're providing advice, but it's very much down to the master, with the advice of the embarked pilot, to get the ship safely into the port.
To monitor an area this big requires a number of different systems.
The systems that we have available to us are radar, obviously, AIS, we use maritime VHF, CCTV, visual, obviously. So basically, as many methods as you can think of, we will use to get information on traffic and to talk to the ships themselves. In general, the difficulty we have in conditions terms is with visibility. We reduce the traffic to single flow to make sure we don't have a conflict between 2 large ships in one of our channels.
Nowadays, it's common in large ports to have such a system.
Thank you very much, sir.
The VTS Centre provides a safety net for ships at risk of collision, but sometimes it's the sea itself which is the enemy. September 1994. The roll-on, roll-off car ferry, Estonia, was on passage in the Baltic Sea. There were 989 people on board. In the early hours of the morning, halfway between Tallinn and Stockholm, the ship encountered extremely heavy weather. Huge breaking waves relentlessly pounded the vessel. The continual slamming of these vast walls of water weakened the assembly of the bow visor, used to load and unload cars. Just after 1 a.m., the hinges failed completely, and the visor was torn off. This exposed the open car deck behind and allowed water to enter the vessel. The effects were catastrophic.
Estonia, what's going on? Can you reply?
My immediate reaction was to try and find a way out, or find a life raft, find a life jacket. I could see the water coming onto the ship. I couldn't see a way of getting off, and I could see my life ending at that point, trapped inside the ship.
The ship capsized soon after. And at 1:50, the Estonia disappeared from radar screens. The ship had sunk to the bottom of the Baltic Sea. Helicopters and nearby ships arrived to help those that had made it to the life rafts. Only 137 people were saved. 852 died. The investigation into the disaster had a profound effect on the design and operation of car ferries and concentrated on 2 areas: bow visor arrangements and stability. In the past, stability had always been a problem on car ferries. This is because they have large open car decks, effectively one huge compartment, stretching the length and breadth of the vessel. If water somehow got onto this deck and moved around freely, the ship could be destabilized. The phenomenon is called free surface effect, and it works like this. As the ship naturally rolls to one side, the surface of the water will stay level. This means that the water gathers on the low side of the vessel. The result is that the ship's center of gravity is raised, which has a destabilizing effect, sometimes to the point of capsize. The sinking of the Estonia wasn't the only time a car ferry had capsized. Just 7 years earlier, in 1987, the Herald of Free Enterprise suffered a similar fate. The ship had just left the port of Zeebrugge in Belgium, carrying 459 passengers and 80 crew.
We arrived by helicopter, we went down in the ship, and it's incredible to see what happened. People were drowning in the ice-cold water. We tried to get them out. It's a terrible thing.
The Herald was less than 1,300 meters from the harbor entrance, but despite being so close to land, many of those on board didn't stand a chance.
The authorities have long since given up any hope that anyone is still alive out here.
193 people died. In this case, the bow doors have been left open, but the results were the same as for the Estonia. Once water was on the car deck, free surface effect took over, causing the ship to capsize. Various solutions to the problem of free surface effect were tried. One of the first were removable bulkheads. These partitions reduce the size of the open spaces on the car deck, limiting how far water can move. But for short journeys, they increase loading time. Another solution, sponsons, are like huge lifebelts for boats, buoyant boxes that fit around the ship to increase stability. But they also increase fuel consumption, and they can make the motion of the ship uncomfortable for passengers. The eventual solution was far more radical and could only be implemented on brand new ships. It required a substantially different basic hull shape. Wider and more box-like under the water, modern car ferries are inherently more stable. The Adventurer was built in 2003. It's one of the most advanced car ferries operating today and employs a wide and box-shaped hull.
The hull shape does make a ship more stable. We are streamlined at the front, but as you come towards the middle, we're very boxy. And just imagine a box in the water, you know? The thinner the box, okay, the more it's going to rock, okay? But the wider the box, the less it will move in a seaway.
As well as having an inherently more stable hull, the Adventurer has been designed with another feature to deal with free surface effect. Drains, or in nautical terms, scuppers. These drains deal with the problem of water on the car deck in the most effective way possible, by getting rid of it.
The important thing is to keep water off that car deck at all costs.
What we have essentially is big drain holes. The water would go down these drain holes into a big holding tank, okay? And the pumps would then be started to pump this water out of this tank. As the water came in, it would be pumped out.
But in the Herald and Estonia disasters, stability was only part of the problem. Bow doors and visors were the other factor. The Estonia used a vertically opening bow visor. These were popular at the time, but had two weaknesses. Firstly, in heavy weather, there's an upward force in the bow visor from the impact of waves, and this imposes a huge strain on the hinges. The second problem was that the bow visor was directly attached to the car loading ramp behind. When the hinges failed on the visor and it fell off, the ramp was pulled down, and this allowed water to immediately enter the car deck. There were no fail-safes.
It was such a shock to everybody, and it was clear that something had to be done. It had to be done very quickly indeed.
Part of the solution to these basic problems was to move away from using bow visors. Most modern car ferries are now constructed using horizontally opening doors. The advantage is that waves hitting the doors push them inward rather than upward, actually making the structure more solid. The second level of protection is to provide a secure watertight bulkhead behind the bow doors. On the Adventurer, this is formed by the car loading ramp. It's entirely separate from the doors, and once raised, is locked in position.
This ramp, when in the fully closed position as it is, forms an integral part of the ship's collision bulkhead. If the outer hull is breached, for example, if we were hit by another ship in the bow area. As long as the bow ramp here integrity is not breached, it should allow no water ingress onto the car deck.
Should anything go wrong with the bow door arrangement, it's vital that the crew know about it. Like the Scandinavian Star, both the Herald and Estonia disasters were made worse by a lack of information.
The Herald and the Estonia didn't even know water was coming into the deck.
The Adventurer and virtually all modern car ferries are fitted with advanced monitoring systems, CCTV, and flooding alarms to alert the crew immediately if water is entering the car deck.
Here we have the water detector alarm. If any water comes onto the car deck, water will flow up into the pipe. There's a sensor inside that detects the water and sets the alarm off both visually and audibly on the hull integrity panel on the bridge, so we can immediately know if there's water on the car decks. Back that up with the visual check on the CCTV.
CCTV system on the ship covers the whole ship, the whole engine room and the whole of the car decks and outside decks. It's very, very beneficial to us in emergencies. If, for example, the bow is breached, you can see straight away down there if there is water.
Systems like this were introduced after the capsize of the Herald. They drastically reduce the chance of a vessel leaving port with its doors open, and also allow the captain to constantly view the status of the bow doors and car deck whilst at sea. Virtually all modern car ferries are built with these improvements, and it's because of what happened to the Herald of Free Enterprise and the Estonia. Thanks to these advances in design, car ferries are now safer than ever before. But ship designers haven't stopped there. There's a radical new type of ship that addresses all of the problems faced by car ferries, the high-speed catamaran.
At the moment, we're travelling from Dunleary to Holyhead on the Irish Sea. We're travelling at 40 knots on the Stena Explorer, which is the world's largest high-speed catamaran ferry, which is 126 metres long, powered by 4 gas turbines, which are the equivalent of aircraft engines.
These 4 engines produce a staggering 100,000 horsepower. They drive 4 of the world's largest water jets, which between them pump out 100 tons of water every second. This gives the Explorer a top speed of 40 knots. It's also hugely stable thanks to the 2 hulls being set 40 metres apart. And because it's so wide, cars can perform a U-turn inside the ship and enter and exit using stern doors. This means it has no bow doors. The Explorer is cutting edge and has every imaginable safety system designed in from the start. But this ship has one safety feature that overrides all the rest. In case of a collision that damages the hulls, it'll stay afloat even when inundated with water.
And wreck the ship, which means taking the bottoms out of both hulls, and the ship will still float. She'll float at the car deck level, which is a very safe position to be in.
The Explorer can do this because she's very light, a result of being designed to operate at high speed. While the Explorer seems to be an ideal solution to the challenges faced by car ferries, there's one problem it faces that's extremely difficult to overcome: fuel consumption. The price for such high speed is reduced fuel economy. As a result, the high-speed catamaran sometimes only operates at reduced speed. There will always be a demand for the unique service that ferries offer, so naval architects keep working to develop the ultimate design. In Norway, there's a radical new ship that one day may provide a solution: the X-bow.
This is a totally brand new concept that does not exist in comparison anywhere in the world.
This futuristic-looking design is already in use on commercial ships, but may soon be implemented on passenger ships.
The most important aspect is better heavy weather performance. You can actually pass through heavier seas at higher speeds.
There are 2 reasons why the design can do this. Firstly, this type of bow has volume much lower down than a conventional bow. This means as the ship encounters a wave, the increase in buoyancy is gradual and constant rather than sudden and rapid, as on a traditional ship. This makes the vessel's motion smoother. The second reason is that the X-buoy is not flared. Conventional buoys curve out at the top. The X-buoy doesn't. This means energy isn't wasted trying to push waves out of the way, so a higher speed can be maintained.
Now what we see here is the traditional offshore bow moving in North Sea heavy conditions at 12 knots. And this is the Ulstein X-bow moving in much larger sea states and even higher speeds than compared to this one. And you can clearly see the difference in how they encounter the waves. Now, the normal traditional bow always tries to push the water up and away from itself, whereas the Ulstein X-bow tries to go through it in a more smooth way, just deflecting water along its side.
In this footage shot in heavy weather in the North Sea, the difference between the two types of ship is apparent. The traditional buoy is lost in a plume of spray as the X-buoy almost glides forward. But testing models of the new design wasn't all plain sailing.
So when we first approached the mold test facility, they were kind of skeptical to the concept because they believed that the ship would probably go under as soon as it hit a wave. So we found that we wanted to test the boat in a developed high sea state where you encountered a big wave in high speeds. So this boat is now moving along at 14 knots, hitting a wave at approximately 14 meters. And even in this wave, the boat survived well. And that was a very good day, actually.
One of the primary advantages of the design is that it reduces the slamming effect of waves on the bow.
If you see the gray spot here and here on this vessel, those are pressure cells that measure bow impact loads. And we've seen that the Ulstein X-bow never have any bow impact loads of significance. Since you don't have that continuous slamming impact, you're not as exposed to structural damage as compared to a traditional type bow.
This is a potential benefit for ferries.
We have a separate design that we are now developing for ourselves, and we know for a fact that loading is going to be significantly less than for a conventional flared bow vessel.
The design has several other assets for passenger shipping. Because it's able to operate regularly in heavier weather, there should be fewer cancelled or delayed sailings. And as the ship is subject to less stress, the manufacturers claim that maintenance costs should be lower. And fuel costs will also be reduced because the design moves more efficiently through waves. Maybe one day, all ships will look like this. Back in Italy, the finishing touches are being added to the much more traditional-looking Ruby Princess. When all the onboard systems have been successfully tested and the ship is handed over, the owners will have a vessel that has been built with knowledge that's been gained over hundreds of years. From safety monitoring systems to watertight compartments, even the most sophisticated aspects of our design can have their heritage traced back to ships that have sailed before.
This process of continual improvement will never stop, nor should it. That's what it's all about.
Although accidents will sometimes still happen, naval architects hope that by learning from the tough lessons of the past, modern ships will sail safely into the future.